Okay, let's start with the session, friends. So today's article is Law of Conservation of Momentum. We all know how we define momentum. Momentum is defined as product of mass and velocity. And then when we talk about law of conservation of momentum, this statement plays an important role over here. So what is the statement for law of conservation of momentum? Let's understand that. So what it says is, when two or more bodies act upon one another, in simple words, they collide with each other. Say for example. So when two or more bodies act upon one another, that means they collide, then in the absence of external force. Now if this happens in the absence of external force, then you can see the total momentum of the bodies of the system, all bodies of the system in a particular direction will remain same or constant. This is law of conservation of momentum, or in simple words, you can also say the total momentum before collision will be equal to the total momentum after collision, provided no external force acts on the system when the collision takes place. So this is how you're supposed to analyze it, okay? So before I show you the next slide, I want you people to quickly make a note of this so that we move ahead. Okay, hopefully you all say it's done, right? Okay, so let's share a new slide here. Okay, just give me a moment. Yeah, so we are supposed to prove the law of conservation of linear momentum. For that, we are considering two spheres. You can see the spheres on your screen. Okay, so before collision, this is the picture before collision. They are moving in a straight line in such a way that u1 is greater than u2. So if this sphere is 1 and this sphere is 2, the initial velocity of sphere 1 is greater than 2, and that means this sphere will ultimately collide with sphere 2. So what happens there onwards? So let us understand the statement first of all, okay, what it states. So when the resultant external force acting on the system of interacting bodies is zero, that means it's an isolated system, then it says that the total linear momentum of the system of the interacting bodies remains constant. Okay, so this is the picture before collision. So we are considering two spheres, say A and B, of masses m1 and m2. Okay, and they are moving with u1 and u2 as initial velocities such that u1 is greater than u2. So if that happens, that means the sphere 1 will ultimately collide with sphere 2, you can see, because u1 is greater than u2. So this is a picture before collision. So before we talk about what happens during collision, please make a note of this slide basically, and let me know once you're done with it. Then we discuss what happens after collision or during collision in a way. So this is a picture showing you what happens during collision. Okay. So mostly you people say done. So I believe you have made a note of this. Then ultimately what's going to happen? The sphere one will, collide with sphere two, right? And then the next picture comes into consideration over here. So during collision, what happens? You can see as u1 is greater than u2, A goes on approaching B, and at certain instant the spheres will collide with each other, something like this. Yeah, so they are colliding. You can see on your screen, they collide with each other. Okay. So what happens during collision? So before we talk about what happens during collision, you can just make a note of this also quickly so that we move ahead towards the next slide. This animation will keep on happening, so please take a note of it, okay? And at certain instant, they are going to collide. So let's see what happens during collision. So before we go to the next slide, please make a note of this. Hopefully, you have noted it down. Yeah, people say yes. So let's move ahead then. Yeah, so this is the picture during collision. Okay, say for example, what's happening during collision. As per Newton's third law, sphere A will exert force on B, that is F. And what sphere B is supposed to do? It is supposed to exert equal and opposite force on A. So obviously, from A to B, if it is F, from B to A, the magnitude will remain same, but the direction will be opposite. So it would be minus F. So this is what will happen during collision. So let's say F be the force exerted by sphere A on B. Then the force exerted by B on sphere A will be minus F. Let T be the time of impact. So when I say T is the time of impact, that means for time T, they stay in touch with each other. And after impact, obviously they will start moving with different final velocities. So let these velocities be v1 bar and v2 bar for both the spheres. So this is the situation which is happening during collision. Please make a note of it before we start framing equations for the given situations. And let me know once you're done with it so that we can move ahead. Yeah, so most of you say done. Let's move ahead then. Okay. So what's happening here is the collision is taking place, and as per Newton's law, A is exerting force on B and B is exerting equal and opposite force on A during collision. And after the collision takes place, they will start moving with final velocities v1 and v2. That's what they are saying. Okay, so let's see. Let's move ahead. So this is what's going to happen after collision. So this is a picture specifying the situation after collision, where you can see sphere A of mass m1 starts moving with final velocity v1, and sphere B of mass m2 moves with the final velocity v2, friends. Okay. Now in the given situation, for sphere B, if we talk about, F is the force, okay, because A was exerting what force on B? So that force was F bar. So you can see, because that force has to be mass into acceleration. But which mass? Because we are considering sphere B, the mass will be m2. Which acceleration? So acceleration of B. So that will be v2 minus u2 by t. So m2 into a2 is F. This is the force acting on B. So simplified, let's take t on one side. So what we get is F bar into t equal to, again we can simplify this. You can put m2 multiplied by v2 minus m2 multiplied by u2 bar. Okay, so this is equation number 1 for sphere B, which we get over here. Now similarly for sphere A, we are supposed to get an equation, but then the force is equal but opposite. Again I say the force is equal. B is also going to exert force on A as per Newton's third law, but then it is opposite in direction but equal in magnitude, and therefore this force is represented as minus F bar. You can see on your screen. So this minus F bar is acting on A, therefore it will be m1 into a1, because we are talking about A. It will be m1 into a1, and a1 can be written as change in velocity of a1 per unit time, that is v1 bar minus u1 bar by t. Then we shuffle the values again. You take t on one side, what you get is minus f into t will be, again m1 can be multiplied by v1, so it becomes m1 v1 bar minus m1 u1 bar, you can see. Now if I want to remove this minus sign over here, you can see what I will do is I'll multiply the entire equation by minus sign. The moment I do that, minus into minus will become plus. Here minus into minus, minus into plus will become minus, and here also minus into minus will become plus. So if I shuffle the equation that way, then ft will be equal to, you can see, you can shuffle the equation, then m1 u1 minus m1 v1. This is what you will get finally. So this is the equation 2. Very important slide, friends. In equation 1, we have the value of f into t. In equation 2 also we have the value of f into t. Now we are going to equate these two equations to prove this law. Before we do that, please make a note of this slide, very important slide, and very interesting to know how we have framed equations 1 and 2 for the cases of sphere B and A respectively. So once you are done with it, let me know so that we can move further to discuss law of conservation of, momentum being derived or proved in this case. So mostly people say they are done with it. So let's take their word and let's move ahead. Okay. So now what, as I said earlier, we are going to equate equation 1 and 2. Why we are supposed to equate equations 1 and 2? Because the left hand sides are same, f into t. So we equate 1 and 2, and what we get is, so equating 1 and 2, these are the two equations 1 and 2 you can see, and we are equating them. So m2 v2 minus m2 u2 should be equal to minus m1 v1 plus m1 u1, or directly you can equate. So you take v terms on one side, so it will be m1 v1 bar plus m2 v2 bar. You take u terms on the other side, so m1 u1 plus m2 u2. What does this mean? m1 u1 plus m2 u2 means the initial momentum before collision of the system. What is this meaning? m1 v1 plus m2 v2, it's the final momentum of the system after collision. So there was no external force acting. They collided on their own, and ultimately we proved that the total momentum before collision is equal to total momentum after collision, and that proves, you can see, momenta is a plural form. Okay, so plural form of momentum is momenta. So this is how we have proved that the initial momentum is equal to final momentum, and thus you can see the total momentum of the system remains constant, that is conserved, and this is how you prove law of conservation of momentum. So before we go ahead towards the examples of law of conservation of momentum, I want you people to quickly make a note of this so that we discuss this law of conservation of momentum and its practical application basically, and then we will be in a position to solve some problems on this concept. Once you are done with it, let me know so that we can move ahead then further. Okay, fine. So most of you say done, so let's move ahead. So again, I repeat, we have proved law of conservation of linear momentum, friends. And what it says is, if no external force acts on the system, the total momentum before collision is equal to total momentum after collision. Okay, fine. So hopefully I've noted this down. So let's try to analyze some examples on law of conservation of momentum. Okay, just give me a moment. Yeah. So the first example, you can see the bullet fired from a gun, or in the animation you can see a cannon fired from the, you know system made for firing the cannonball basically. Cannonball fired from cannon basically. Okay, a bullet fired from a gun. Okay, that's an example of law of conservation of linear momentum. Let's understand how. Okay, so please just make a note of this, and we will think about how law of conservation of linear momentum is applied in this case. All right. Hopefully, I've noted down this picture so that we move ahead and I explain you how law of conservation of momentum is applicable for this example. Okay. So people say yes, they have noted it down. So let's move ahead. Okay, please wait. Yeah, Reva, we are waiting. You tell us. Okay, so, fine. Now let's understand how the law of conservation of momentum is applicable over here. Yeah. So what happens is when a bullet is fired from a gun, you can see the gun recoils. Bullet is fired from the gun, bullet moves forward, the gun moves backward. Before the bullet was fired from the gun, everything was at rest, so the initial momentum was zero. But when the bullet is fired from the gun, what is happening is the bullet moves forward and the gun recoils with some velocity and it moves backward. Same is the case over here in this picture. You can see the cannonball moves forward and the cannon moves backward. Prior to the ball being fired, everything was at rest, so the total momentum was of the system was zero. So the initial momentum of the system in both the examples or both the cases is zero. Now what happens when the bullet is fired or the cannonball is fired from the gun? You can see, okay, so this is the situation where this person is firing the bullet from the gun. So in that case, let's understand the first situation. Before firing, the gun and the bullet both are at rest. Hence, the total linear momentum is zero. That's what I said. What will happen after firing? So after firing, the total linear momentum will be, okay, after firing, the total linear momentum in this case would be m1 v1, where you can see, v1 is the speed of the bullet and m1 is the mass of the bullet, final velocity of the bullet, and m1 is the mass. M2, you can say either, or you can say M2 is the mass of the bullet and V2 is the speed. M1 is the mass of the gun and V1 is the final speed of the gun. But both are directed opposite, you can see. So this is the direction of momentum, final momentum of the cannonball, and this is the direction of the final momentum of the cannon. Or you can see for the gun, this is the direction of the momentum, final momentum for the bullet, and this is the direction for the momentum, final momentum of the gun. So what are these two things doing? So vectorally, if you add v1 and v2 are opposite, so they will nullify each other, they will cancel each other, and then you can see, you apply law of conservation of momentum, the total momentum has to be zero. In that case, one has to nullify other, so the final momentum also has to be zero. So zero has to be equated to this as per law of conservation of momentum, you can see. So which employs, so V2 will be equal to, yeah, minus M1 by M2 into, here it should have been V1, okay, wrongly mentioned over here, V1. So V2 is negative of what V1 will be, and therefore they will nullify each other, and then final momentum is also zero. This is how you are supposed to understand law of conservation of momentum while solving problems. Why it has become zero, final momentum? Because the momentum forward has nullified the momentum backward. And initial momentum was zero, final momentum is also zero. And therefore this equation comes into picture. Now in this equation, what correction you are supposed to make? So V2 is equal to minus M1 by M2 into V1. Okay, that's the correction you're supposed to make over here. So this negative sign shows that V2 and V1 are exactly opposite when the gun recoils. That is, the gun recoils, right? Therefore opposite. And as M2 is greater than M1, very much greater, V2 will be very much greater than V1. So you can see the recoil velocity of the gun is very small comparatively, and the velocity of the bullet with which it moves forward is very high. You can see recoil velocity will be very less. So the reason is given in the last point. Why? Because M2 is very much greater than M1. You can see in this equation itself, if you put M2 as very much greater than M1, Obviously, what can you say about V2? V2 will be greater than V1, very much greater. The bullet has to move forward very fast. That's how it can, penetrate human body and can be fatal. That's the purpose of bullet being fired from the gun, right? So that's how law of conservation of momentum is active in this case. Here in the entire slide, everything is correct except this notation. Here it should have been V1, okay? So please make a note of this. And please make a note of this slide also before we move forward. And let me know once you're done with it. Hopefully you people say you're done with it. Good. So if you have understood this example of bullet fired from the gun in terms of law of conservation of linear momentum, right? So we move ahead then. Let me know if you are comfortable with this situation, because these are the situations which we are going to use while solving problems, friends. So please share your views on this. If you are comfortable with this, I can explain you another example of law of conservation of linear momentum. Yeah, okay. So Swarali Ananya says yes. Reva says yes. Fine. So let's move ahead then. Let's talk about the second example when we think about law of conservation of linear momentum, and that is motion of a rocket. So here also, before the rocket is being fired, you can see the initial momentum is zero. You can quickly take a note of this so that you have a set of notes basically with you along with the pictures, because at times pictures also make things very clear. Okay, hopefully you have noted this down. Let's move ahead then. So should we start discussing motion of rocket? Let me know. Okay. Initially, you can see the rocket is at rest. Therefore, the initial momentum of rocket will be zero. All right. But then what happens when the rocket is being fired? Let's see. Yeah. In rocket, oxygen is burnt in the combustion chamber. So this is how it is. Okay. So oxygen is burnt in a combustion chamber. So this is the inner chamber is combustion chamber over here. All right. So this is a simple diagram, layout of rocket. What lies where. Okay. So hopefully you are quickly noting it down so that we move ahead. So what happens? The hot gases are ejected. Okay. So again,
Sir,
yeah, yeah.
can we show the picture of that
Yeah,
rocket?
yeah. I'm on that picture. Okay. So here you can see the gases come
Yes,
from
sir.
this. Yeah, the gases come from the nozzle. So they will push the ground, and the ground will push the rocket as per Newton's third law, isn't it? So initially, when this process was not happening, the initial momentum of the system was zero, and when the process starts happening, what you can see, the gases they move downwards to the nozzle, and the rocket moves upwards. So in that case, what happens? Let's understand. The hot gases are ejected through a small opening, that's what I said, with high pressure and high speed. As a result of it, you can see there is a large momentum of gases produced in the backward direction. Backward means downward direction here in this case. So obviously it's a case of action reaction. So gases they move backward or downwards. Reaction is rocket moves forward or upward. You can see. Okay, so please make a note of it before the picture vanishes. Once you're done with it, so easily we can apply law of conservation of linear momentum over here. Initially, when the action reaction is not taking place, everything is at rest, so we can say the initial momentum is zero. But then once the ignition takes place, then what happens? Okay, let's see. Yeah, so this imparts forward momentum to the rocket, and rocket moves upwards with high speed. This is how it's going to happen, right? But then initial momentum was zero. Now there are two momentums after the ignition takes place. Rocket has momentum upward, gases have momentum downward. So they nullify each other. So in a way, final momentum is also zero, even if the motion is taking place. So that's how you have to understand law of conservation of linear momentum. Okay, you can see change of momentum is constant, uniform. The force is also constant. And due to escaping gases, the mass of the rocket goes on decreasing and the velocity and acceleration goes on increasing. Why the mass of the rocket will go on decreasing, friends? Because the fuel is the parameter. The fuel reduces after consumption and therefore mass reduces, acceleration goes on increasing, you can see. So you need to understand this, the velocity and acceleration of the rocket increases, and then finally you can see the rocket will attain a very high velocity which is needed for the rocket to escape Earth's atmosphere and go to a requisite height in the space. So here motion of rocket involves two laws, Newton's third law as well as law of conservation of linear momentum. Please make a note of this. Very important slide. And let me know once you're done with it. Okay. Hopefully, I assume if you are done with it. So let's see. Okay. Revising done. So let's move ahead then. Okay. So again, what I said, let me recall a few points regarding this slide before we move forward. Initially, the combustion is not on. So the final initial momentum is zero. When the combustion is on, the gases escape downwards, rocket moves forward. The action reaction pair occurring there as per Newton's third law. So the gases they push ground, then the air, and then which in turn pushes the rocket upwards. There are two momentums. Upward momentum of rocket is nullified by the downward momentum of gases. So the final momentum in the entire process will keep on becoming zero. So the initial momentum was also zero and final momentum is also zero. So this is the concept in accordance with law of conservation of linear momentum. And then I did talk about the mass of the rocket goes on decreasing and correspondingly the acceleration goes on increasing, which results in a very high velocity which is needed for a rocket to escape Earth's atmosphere. Hopefully these things are clear to you people. Okay. The next example can be explosion of a bomb. Okay, that's again will be as per law of conservation of linear momentum. Let's understand how. So initially, if I talk about a bomb, so it's not exploding, right? So initial momentum is zero. So let's say initial momentum of this bomb is zero. But then what happens after explosion? You all know if it explodes, what's going to happen? So when a bomb is at rest before explosion, sorry, the linear momentum is zero. We all agree with this. But when the bomb explodes, then what's going to happen? It will break into number of pieces and different pieces will move with different momentums. You can see. Say for example, initially the bomb was not exploding. So the momentum was zero. When it explodes, you can see in the diagram, one piece moves upward with some momentum, other moves downward. One is nullifying other, third is nullifying fourth. So, in general, every particle's momentum is getting nullified. So in a way, the final momentum also can be considered as the vector sum of the linear momentum of all these species. And therefore it is also zero. Okay. So just try to understand. Initial momentum was zero. Why it had not exploded? Final momentum is zero. Why? Because it has exploded into pieces. But one piece's momentum is, one piece momentum is going to nullify the other piece. In this way, the total momentum after explosion can also be considered as zero. Make a note of this before I actually explain you in terms of equations what exactly happens over here. Let me know once you're done with it. Okay. Let's see. Yeah. So most of you say yes. So let's move ahead then. Let's understand what happens. Okay, so let's say it can explode in n number of pieces, but just for the sake of convenience, I consider that it has exploded in 4 pieces, and the masses are m1, m2, m3, and m4, and their velocities would be v1 and v2, v3, and v4 correspondingly. So the linear momentum of the 4 species would be given by, initial, you can see p1 will be m1 v1, p2 will be m2 v2, p3 will be m3 v3, and p4 would be m4 v4. Okay. Now, as no external force is acting on the system, the total linear momentum is conserved. That's what we have discussed. So let's say total momentum has to be equated to 0. So what was the initial momentum? 0. And that has to be equal to final momentum. So in final momentum, this would be the equation m1 v1 plus m2 v2 plus m3 v3 plus m4 v4. Actually, you can extend it to n number of pieces, but here we have considered only 4 for our convenience. Now what's going to happen? The directions of v1 and v1, v2, v3, and v4 will be such that they will nullify each other. So whatever was the initial momentum, that was 0, would be the final momentum, that is 0. Therefore, this equation is being considered. So while solving problem, this equation will play an important role. So it's not only about explosion of bomb. Most of the collisions, law of conservation of linear momentum is being followed, and this is to be used while solving problems. Please make a note of this before I actually explain you how we solve problems based on this. Once you are done with it, let me know so that we move ahead towards dealing with the problems, friends. Yeah, so most of you say yes. Good, we are done with it then. Okay. Fine. So most of you say yes. So what we will do now, we have understood the concept of momentum, law of conservation of momentum. We will try solving problems on this. So give me a moment where yeah, I present you the question to solve, based on law of conservation of momentum. Now, what is this question telling you? Calculate the recoil velocity of a gun of mass 5 kg which fires a bullet of mass 50 gram with a velocity of 500 meter per second. So you are supposed to find the recoil velocity of the gun. And once that is done, there is one more additional aspect you have to calculate over here. That is the impulse. Calculate the impulse given to the bullet. It gives to the bullet basically. So let's say the given things are M1 is 5 kg. The mass of the gun M1 is 5 kg. M2, the mass of the bullet is 50 gram converted into kg multiplied by 10 raised to minus 3. So M2 becomes 0.05 kg, friends. Now, by the principle of conservation of linear momentum, just now we have framed the equation. What was it? M1 V1 would be equal to M2 V2. Both have to be equal. Then only they will nullify each other. So whatever is the momentum of gun should nullify the momentum of bullet. That means they should be equal and opposite, so that their total will become 0. So if you take this term over here, then it has to be equal to 0. Alright, so from this you can actually work out the unknown values. M1 5, V1 is to be estimated, M2 is 500 into, V2 is 500, that's what is given. The 0.05 is M2. From this, V1 is estimated to be 5 meter per second. So this is the velocity with which the gun will recoil back. Okay. This is the recoil velocity. Then initially they say the bullet is at rest. Obviously it is not fired, means the bullet is at rest. And you are supposed to find out impulse. So impulse from impulse momentum theorem is nothing but change in momentum. The change in momentum is final momentum minus initial momentum of the bullet. Therefore, J will be m2v2 minus m2u2 because we are talking about bullet. Had it been about gun, it would have been m1 m2 m1 v1 minus m1 u1. But we are talking about bullet, so m2 v2 minus m2 u2. So substitute the values then. You know m2 is 0.05, v2 500, and m2 into 0 because initially the bullet was at rest. This gives us the impulse equal to 25 kg meter per second. So you can see the recoil velocity of the gun is 5 meter per second. This is what we have estimated. Whereas the change in momentum is nothing but the impulse. So impulse on the bullet is this much, 25 kg meter per second. Please make a note of this so that we can solve one more problem which will ensure that this concept is clear to us. Let me know once you're done with it. Okay, most of you say done. Yeah. Okay, fine, no problem. So let's move ahead then. Let's solve one more problem on law of conservation. Just give me a moment. Okay, just give me a moment. Yeah. Here they say, okay, what all things are given to you? Concentrate in this problem. A body of mass 2 kg traveling with a velocity of 4 meter per second makes head-on elastic collision. Okay, what is elastic? That would be the next part of discussion, but let's understand it here. Let's try dealing with it. Okay. So what is elastic collision? This is something which we have to study. So this comes under types of collision, friends. So, as of now, I give you this question for you to practice because we are supposed to discuss elastic collision in this, and we will talk about elastic collision in the next session, not this session. So therefore